All right, so this is chapter 9, which is all about stoichiometry. And stoichiometry really deals with how we can go between different substances. Up until this point, we've only stuck with one substance, maybe going between grams and moles or grams to moles to atoms, that sort of thing. But now we're going to be able to cross into a different substance. And so just to review, we can use Avogadro's number to go from moles of a substance into atoms, molecules, or ions. We can use the average atomic masses off the periodic table to find the molar mass, and the molar mass allows us to go from grams to moles. Important thing to remember here is that the grams that you find from the periodic table always need to go with 1 mole. Today we're going to introduce using the coefficients from the balanced chemical equation. And one mistake that I see all the time is that students like to put the coefficient with the molar mass as well. So maybe put a star or make a note to yourself that molar mass always gets 1 mole. Okay, it's not going to make sense until you actually see where we use coefficients, but I do need you to keep that in the back of your mind. We can always still use these relationships as conversions with our unit conversions, but today we're going to add in how to involve coefficients to go between substances. So, stoichiometry is how we compare relationships between different substances. So, in order to do stoichiometry, we always need to have that balanced chemical equation. Remember, to get a balanced chemical equation, first you have to have correct formulas for each substance. Then take a look. Usually you balance your polyatomics and metals first, and then move to nonmetals, and then oxygen and hydrogen and diatomics. So keep that all in the back of your mind. You're still going to have to balance equations and be able to write formulas. And if you can't quite balance a chemical formula, then stoichiometry is going to be very difficult. So let me know if you need help with that. Once we have a balanced chemical formula, we're going to be able to set up what are called these mole ratios. We're also going to be using roadmaps in stoichiometry. We've used them a little bit before with our conversion factors and with our more simple conversions like mass to moles or moles to atoms or moles to molecules to atoms, that sort of thing. We've used the roadmaps a little bit, but now it's going to be very important to use roadmaps to figure out where we're coming from and where we're going. When we use these roadmaps, I need you to include the substance. Okay? You can't just say grams to mole to mole. I need to know what substances you're dealing with there. So be sure when you are doing these roadmaps that you include the substances there. So again, here is a look at our mole map. We're really going to hone in on the middle of this section for this lecture. So right in here is really where we're going to hone in on. We're going to be first starting with moles to moles. Then we're going to go grams to moles to moles. So 3 things. We can also go grams to mole or moles to moles to grams. And then lastly, we're going to go all the way across grams to moles and moles to moles and moles to grams. So we will be going all the way across here by the end of this lecture. So the mole ratio is, you might hear me call it the mole bridge. This is the bridge that takes us over from one substance to another. And so if we take a look back at, the mole map, there's only one way to get from substance A to substance B, and that's through the moles. So you have to be able to start with, the substance A, get us to moles, and then when we want to convert, the only place to go from moles of substance A is into moles of substance B. And so with these mole ratios, they come from the coefficients in the balanced chemical equation. So you can see there is the equation for how we make water. We have 2 hydrogens and an oxygen being used to make 2 waters. And so we can think about that in terms of atoms, molecules, but the more useful way is moles. So there are 6 different ratios you can set up for this particular equation. You could say that we have 2 moles of water per 2 moles of hydrogen, and you can position that one of 2 ways, which you see first down here. You could have 1 mole of oxygen to make 2 moles of water, which you can see in these 2 different setups here. Or we can compare our reactants. So you can have 1 mole of oxygen is needed with 2 moles of hydrogen there. And please just note that you can flip them however you need for your roadmap. Remember that we always want to put the unit that we're getting out of on the bottom, and the unit that we'd like to try to get into is on the top. So we're going to have to figure out which way to position them to get them to all match. So again, I sometimes call this the mole bridge. So if you ever hear me talk about the mole bridge, it's going from moles of one substance into moles of another. So when we're trying to do mole-to-mole conversions, you need to balance the chemical equation, read the problem and determine what is given and what needs to be solved for. You could be given 2 reactant substances, 2 product substances, or 1 reactant and product. Please do not get hung up on the fact that it sometimes may not make sense to you why we're given 2 reactants to solve for, or 2 products are in the problem, or sometimes to students it doesn't make sense why we would be dealing with 2 reactants or 2 products. A lot of times it makes more sense to deal with a reactant and a product, but we can do any sort of thing. The side of the arrow the substance is on does not change the process. So we do the same process no matter which side of the arrow these substances are on, meaning reactants or products. You're going to start with your given and use the proper mole ratio to get out of the old unit and into the new. Remember that the old needs to be on the bottom and the new needs to be on the top. So this next problem asks, how many moles of water can be produced if we use 4 moles of oxygen? Well, we're going to start with moles of oxygen and move into moles of water. So we start with our 4 moles of oxygen. This was given from the problem. So we're going to start there. Then we're going to put moles of oxygen on the bottom because that's what we would like to cancel. And then we're going to be left in moles of water up on the top. How did we get the 2 and the 1? Well, the 2 came from water. And then the 1 came from the fact that there isn't anything in front of oxygen makes it a 1. So we've got to remember that fact there. So then to get that math, we take 4 times 2 to get us that 8. Down on the bottom, we're trying to figure out how many moles of oxygen are necessary to react with 0.2 moles of hydrogen. Again, it doesn't matter that we have 2 reactants here. We are going to start here with the 0.2 moles of hydrogen. And then on the bottom, we need moles of hydrogen. On the top, we need moles of oxygen because that's what we'd like to get into. Again, we take a look at our chemical equation. We get the 2 there for our hydrogen. We get the 1 there for our oxygen. And so we take 0.2 divided by 2 to get us 0.1 moles of oxygen. Now, this one here, we've got sodium carbonate with iron chloride to create sodium chloride and iron carbonate. Iron 3 carbonate, I should say. And the first question asks how many moles of iron 3 carbonate will be produced if 5.5 moles of iron chloride are used, and then how many moles of iron chloride are needed to react with 2.4 moles of sodium carbonate. So again, please don't let it get hung up on you that the second problem we're dealing with 2 reactants. That's totally fine. The first thing you're going to have to do is balance that chemical equation, and then you can go ahead and try to answer those. All right, so if we take a look at our answers here, this first one, we are starting with moles of iron chloride. We are going to cancel out our moles of iron chloride here, and then we'll be left in moles of iron carbonate. And so we take 5.5 divided by 2, and that gives us about 2.8. And then the next one, we start with 2.4 moles of sodium carbonate. We get out of moles of sodium carbonate, and we get into our moles of iron chloride here. It's a 2 to 3 ratio. All right, so if we go ahead and try to balance this out, what we're going to need is we are going to need 2 iron chlorides. We're going to need 3 sodium carbonates, and we're going to need 6 sodium chlorides. So in this one here, we are going to start with our moles of iron chloride, and then we will get out of moles of iron chloride into moles of iron carbonate, which is what we want there at the final answer. We get the 1 from our iron chloride here. We get the 2 from our iron carbonate, and then the 2 from our iron chloride. And so we take 5.5 divided by 2, and that gives us roughly 2.8. In the next problem, we're starting here with 2.4 moles of sodium carbonate. We get out of moles of sodium carbonate and into moles of iron chloride. We get the 3 from our iron sodium carbonate and the 2 from our iron chloride. We take 2.4 times 2 divided by 3, and that gives us our 1.6. All right, the next problem here would be a mole to mass conversion. So this one, we are going to start with grams, and we're going to go to moles of the same substance, and then we're going to cross that bridge using the mole bridge. So we have to remember that we can find the molar mass of a substance from the periodic table. If we, for whatever reason, were given mass in something other than grams, let's say we were given our units in milligrams, you've just got to first take the milligrams to grams, and then you can start that. If we were given kilograms, you would want to take it from kilograms to grams, and then we could start that problem. So make sure that you get to grams in order to be able to use molar mass. That doesn't happen a ton, but you may see it. So if you are ever given a mass that's not in grams, make sure you get it to grams before you start the problem. Now, again, you need to find this by calculating the molar mass. And the biggest issue I see here is that students like to use the coefficient in the mole bridge, but they also like to somehow change up that 1 mole here with the grams. So let's say I've got water. Water is 18.02 grams per mole. A lot of students may start to change this from 1 mole, and they might put whatever the coefficient is in the problem. So please don't do that. You always need to just stick with the molar mass in 1 mole. The only time you're going to use the coefficients is when we are dealing with that mole bridge. Moles on top and bottom of that conversion. So we can start with grams, go to moles of the same substance using the molar mass, and then we're going to go from mole to mole using our mole bridge there. So this is what it looks like here. Let's say we have sodium carbonate and calcium chloride. We're going to make calcium carbonate and sodium chloride. It asks how many moles of sodium chloride can be produced by reacting 20 grams of sodium carbonate. So we need to start here with grams of sodium carbonate and go into moles of sodium carbonate. Then we can finally go into moles of sodium chloride. So sodium carbonate to moles of sodium carbonate, we need to use the molar mass. So you can see the molar mass math down in the bottom left-hand corner. The molar mass of sodium carbonate is 105.99. And then from there, we can go from moles of sodium carbonate into moles of sodium chloride using that mole ratio, or what I sometimes call the mole bridge. So starting here with our 20 grams of sodium carbonate, we need grams of sodium carbonate on the bottom and moles of sodium carbonate on the top. So we cancel out grams of sodium carbonate using that molar mass that we just calculated from over here. Then we always use a 1 when we're dealing with molar mass. Okay, that's where I sometimes see an issue. We need to cancel out moles of sodium carbonate, so that needs to be on the bottom, and we're left with moles of sodium chloride on the top. So in this math problem in your calculator, you would do 20 times 2 divided by 105.99, and we get 0.377 moles of sodium chloride. In this case, we're going the opposite way, kind of. So we're starting with moles, then we're going to moles of a new substance, and then grams at the end. Nothing really changes other than the fact that you need to start with moles, do the mole bridge first, and then the molar mass second. So this one, we're using the same exact equation, except now it's asking how many grams of calcium carbonate are produced if 0.585 moles of sodium chloride are produced. So again, we're dealing with 2 products on this problem, which is totally fine. So we're starting here with moles of sodium chloride, and eventually we're trying to get into grams of calcium carbonate. So we start here with moles of sodium chloride. We go to moles of calcium carbonate using our molar ratio. So we get out of moles of sodium chloride into moles of calcium chloride. We don't want to stay in moles of calcium chloride. We want to get to grams. So to get out of moles into grams, we're going to use that molar mass conversion. So out of moles into grams from our molar mass math down in the corner. And so here we take 0.585 times 100.09 divided by 2, and we get 29.3 as our answer there. So let's practice this. You're going to balance the following chemical equation and then answer the following questions. So we've got zinc reacting with hydrochloric acid to produce hydrogen gas and zinc chloride. The first one asks how many moles of zinc chloride can be produced if 12.5 grams of hydrochloric acid are used. And the second one asks how many grams of hydrogen can be produced from 0.148 moles of zinc. So balance it first, then do the two problems. One is like the first problem I showed you, and the other one is like the second. So one goes grams to moles, the next one goes moles to grams. All right, so if we take a look here, all that needs to be done to balance this is a 2 for hydrochloric acid. And once we have that all set to go, we can take a look at our answers here. In the first one, we need the mass of hydrochloric acid, which is 36.46. We're going to start with moles of hydrochloric acid and get us out of grams of hydrochloric acid into moles. Now, please take a look. The only time you are going to use that 2 is in our mole ratio. You do not use a 2 here with our molar mass. It always gets a 1. So we get out of moles of hydrochloric acid and into moles of zinc chloride by using that mole-to-mole ratio, which comes from the coefficients, a 2 there and a 1 there. And so we end with 0.171 moles of zinc chloride. The next one here, we're starting with moles of zinc, trying to get to grams of hydrogen. So we start here with moles of zinc, get us out of zinc into hydrogen. Then we can get us out of moles of hydrogen and into grams of hydrogen. And so we take 0.148, and in this case times it by 2.02, and we get 0.299. All right, and the last and the most extensive type of problem that we deal with in this stoichiometry unit is the mass-to-mass conversions. So sometimes you will hear me call it a grams to moles to grams. If you hear me say that, that's what I'm talking about there in that map. This is probably one of the most useful ones because we know we don't have a instrument to measure moles. So in all reality, grams are one of our most useful things to actually measure with. In order to do this, we need to have the molar mass of each substance, and we must also use the mole ratios from the balanced chemical equation. Down there is the general formula for what we would do here. We would go from grams of A to moles of A by using the molar mass of A. Then we can go from moles of A to moles of B using the mole ratio from the chemical equation. And then we can go from moles of B to grams of B using the molar mass of B. So here is an example. We've got nitrogen plus 3 moles of hydrogen, giving us 2 moles of ammonia. NH3 is called ammonia. How many grams of NH3 can be produced from 875 grams of hydrogen? So we're going to start here with grams of hydrogen. That was given to us in the problem. Our end goal here is grams of NH3 ammonia. So to get there, we need to go from grams of hydrogen to moles of hydrogen, then from moles of hydrogen to moles of ammonia, and then from moles of ammonia to grams of ammonia. So we need to find the molar mass of both things, so you can see that down in the corner. Since we're dealing with H2 here, we need to double the molar mass of hydrogen, so it's no longer 1.01 for this type of problem, it would be 2.02. And then ammonia would be 17.03. So we start here with our grams of hydrogen. We're going to get out of grams of hydrogen and into moles of hydrogen. Please again recognize you get 1 mole of hydrogen per 2.02, not 3. We get out of moles of hydrogen into moles of ammonia by using our molar ratio. So looking up at the equation, the 2 goes with NH3 and the 3 goes with H2. Out of moles of NH3 and into grams of NH3 using the molar mass that we calculated. And so in this one, we would take 875 times 2 times 17.03 divided by 2.02 divided by 3. And this makes an incredible amount. We get about 4,920 grams of ammonia produced. All right, so this practice problem is dealing with the decomposition of sodium hydroxide. Again, that just means that we take sodium hydroxide and we break it down. And in this case, we're going to produce sodium oxide and then water. This question asks how many grams of water would be produced if 4.55 grams of sodium hydroxide was decomposed. So please don't let that terminology of decomposed get to you. Really what this one's asking is if I have 4.55 grams of sodium hydroxide, how many grams of water can I make? So balance the equation, and then we're going to go from grams of sodium hydroxide to moles of sodium hydroxide to moles of water to grams of water. Now, if we want to go ahead and balance this, I need a 2 in front of sodium hydroxide, and that's about it. This is what the solution looks like. We've got our molar mass calculations here on the left. We've got sodium hydroxide is 40.00 grams per mole, and water is 18.02. So we start here with grams of sodium hydroxide, and we are getting out of grams of sodium hydroxide into moles using our molar mass. Again, please use a 1 there. Then we get out of moles of sodium hydroxide into moles of water, and we get that from our coefficients. There's a 2 in front of sodium hydroxide and a 1 in front of water. We get out of moles of water and into grams of water using our molar mass. And so in our calculator for this one, we would do 4.55 times 18.02 divided by 40 divided by 2. All right, and the last part of this unit is probably the most difficult for students to grasp. It's because these problems get pretty extensive and pretty long. We're going to be dealing with reaction yields. And when we think about reaction yields, what I want you to think about is how much product can actually be made. We can do a calculation all we want, but in the end, usually not as much product is made as we think is going to be made. And that's okay. There's things that can happen. But we also should be able to expect, or we should be able to calculate a relative amount that should be able to be expected. And so the relative amounts of reactants and products are given based on those stoichiometric molar ratios. And we, again, can go between any of our different relationships. So you can go between reactants, products, or reactants and products. And so if we think about one of our first things that we should talk about here is thinking about how much can actually be made. This is called limiting versus excess reactant. So consider we're making grilled cheese sandwiches. It takes 1 slice of cheese and 2 pieces of bread to make 1 sandwich. If we were provided with 28 slices of bread and 11 slices of cheese, we can only prepare 11 sandwiches. You have more of one thing, but one thing stops you from making more. So we would use all of the cheese and we would have 6 leftover pieces of bread. So the number of sandwiches prepared has been limited by the number of cheese slices. We would call cheese the limiting reactant at this point. And the limiting reactant will always be entirely consumed. It's the thing that you have fewer of, and so it's going to stop that reaction from taking place. If we could, we'd like to make more sandwiches, but we can't because we're limited by those 11 slices of cheese. Now, the bread slices are what we call the excess reactant. That's because we have more of that thing. And so typically in reactions, we have one thing that we provide a little bit more of excess to make sure that the reaction completely takes place. And then one is a little bit limited. However, you don't want to make them too far apart because chemicals cost money. And so we want to be able to calculate this all out to figure out what the perfect amount is. So a limiting reactant, we really think about this in chemistry as the one that's going to stop our reaction from continuing. So eventually, at some point, all of one substance is going to be used up. Let's imagine making hydrogen chloride gas. If we take hydrogen and chlorine and react them together, we're going to get hydrogen chloride gas. Let's say we want to try to combine 3 moles of hydrogen and 2 moles of chlorine. What we can do is we can, in this case, we can kind of take a basic look and think about, okay, 3 moles of hydrogen would create 6 moles of hydrogen chloride. And if we had 2 moles of chlorine, it would make only 4 moles of hydrogen chloride. And so here, the one that's going to make the less amount is known as our limiting reactant. This is how we do it with stoichiometry. You would start with the moles of each reactant separately, and we're always going to go to the same product. And so in this case, we're dealing with hydrogen chloride. That's our only product in this case. And so we would go to moles of hydrogen chloride. Now, the chlorine will be consumed once we make 4 moles of hydrogen chloride. However, we're going to have a little bit extra hydrogen remaining. So the hydrogen would be our excess reactant. We have more of that because we can't make as much hydrogen chloride with that. The one that always makes the least amount is known as our limiting reactant. The one that makes more, or could be able to make more based on our math, is known as the excess reactant. So this is what it kind of looks like. We've got some hydrogens and some chlorines, and those are going to come together, and we're going to make some hydrogen chloride, and we're going to have some leftover hydrogen at the end. So how do we go about finding limiting and excess reactants? So when a problem gives you the amount of both reactants and asks you to figure out how much product is made, we're going to have to do a little bit more math. If the problem just states the amount of one reactant, then it's a simple problem that we just went through, the mass to mole to mass, or gram to mole to gram conversion, okay? But if we give the amount of both reactants, that's where we're going to have to do a little bit more math. So we're going to need to do 2 different problems to figure out how much product can be made. We're going to run 2 calculations to get to the same product in unit. I'm making this generic because once we get to gases, we're going to have some of these problems again, and same with solutions. So sometimes we're not always going from grams to moles to moles to grams. In this chapter we will, but in the gas unit and the solutions unit, we will further expand on our stoichiometry and we won't be dealing with that. So that's why I'm keeping this a little more generic, is because sometimes we will maybe need to go to liters of solution, milliliters of solution, or liters of gas, for example. So I do want to just kind of keep this generic. So you're always going to start with whatever given amounts of your reactants you are. That's where your roadmaps start for 2 different problems. So let's say I get grams of one reactant and grams of the other reactant. We're going to start there with 2 separate roadmaps. And then we always want to go to the same ending point for our product. Let's say that the problem was asking for grams of copper. So in that case, you would want to run both of those problems to grams of copper. So let's say we are starting with grams of A. You would want to go from grams of A to moles of B to moles of copper to grams of copper. And then let's say we're given grams of B. You would do grams of B to moles of copper to grams of copper. So you always want to end in that same point. I would recommend looking in the problem, figuring out which substance we want to get to and what units we want that to be in. So here are kind of some numbered steps. Figure out what substance and unit the answer is looking for. You're going to write 2 separate roadmaps, starting with the given amount of reactants and ending with the substance and unit from number 1, step number 1. So always start with whatever given units and amounts of the reactants you're given, and then always run to the same substance and the same unit that you just figured out. You're going to run those 2 stoich problems using your roadmap. So run the actual math, canceling out units. So units on the bottom cancel with units on the top. And then the smaller of the 2 answers is the amount of product that can actually be made. So one number is always going to be smaller than the other. That's the amount of product that can actually be made. That's the one that you need to circle as your final answer. Now, the reactant that gave the smaller amount is what we call the limiting reactant, and the reactant that gave the larger amount is known as our excess reactant. All right, so this problem here is asking us how many grams of water can be produced if 4.5 grams of hydrogen reacts with 15 grams of oxygen. So what we're trying to get to for both of our products there is we're trying to get to grams of water. So we're starting with two different separate grams of reactants, and both of them are trying to get to grams of water. So here's what our roadmaps look like. We're starting with grams of hydrogen, going to moles of hydrogen, to moles of water, to grams of water. And then we're going to start with grams of oxygen, go to moles of oxygen, to moles of water, to grams of water. So if we take a look here, we're starting with 4.50 grams of hydrogen for our first one. We're getting out of grams of hydrogen into moles of hydrogen. How did I get 2.02 for our molar mass? Well, 1.01 times 2 gives me 2.02 grams per mole. I get out of moles of hydrogen and into moles of water by using our molar mass or our molar ratio, our mole bridge. So we have a 2 in front of each of those. Then we get out of moles of water and into grams of water. And you might be asking again, how did I get 18.08? Well, we have two hydrogens. We've got our oxygen, which is 6.00, which gives me a total of 18.02 grams per mole for my water. So I get a final answer, or final calculation, for this one to be 40.2 grams of water. So with 4.5 grams of hydrogen, I theoretically could produce 40.2 grams of water. My next one, I'm going to start here with my grams of oxygen that was given in my problem. I am going to get that out of grams of oxygen and into moles of oxygen. I got my 32 by taking 16.00 times 2 to give me that 32 grams per mole for my oxygen's molar mass. I get out of moles of oxygen and into moles of water using our coefficients. And then I get out of moles of water and into grams of water using, again, that same molar mass. So the nice thing here is if you find the molar mass of your product, you're going to use it in two places. This one, however, when I use 15 grams of oxygen, I'm only going to produce 16.9 grams of water. And so that there is my limiting reactant. That limits how much I can produce. And so in this case, the one that I want you to circle as your final answer would be this. I would want you to circle 16.9 grams of water. That's how much is actually being produced. Now, I also need to take a look. The one that gave me the lesser amount, if I go back and take a look at my reactant that gave me the lesser amount, that is called my limiting reactant. And then the one that gave me more, that is called my excess reactant. That's what LR and ER stand for at this point. Now, we can take this a step further and we can figure out how much of that excess reactant is left over. So we figured out how much product was made. Now let's figure out how much of that excess reactant is left over. In our sandwich problem, we had 28 slices of bread and 11 slices of cheese. So we were able to make 11 sandwiches. That means we only used 22 pieces of bread. We were given 28 slices of bread, but we only used 22, so we had 6 left over. That's what we're going to be doing in this problem here. So for this one, we are going to first need to always find the limiting and the excess reactant, doing the same process that we just did. Then once we know the excess reactant, we're going to figure out how much of that was actually used. So here are the steps. You're going to start with the amount of product that was actually made. So the lower of the two amounts of your calculations, start with that. Then you're going to work backwards to find the amount of the excess reactant that was actually used. Okay, so essentially you're going to start with a smaller amount of product made and run the problem back to the excess reactant units. So usually in these problems, it's going to be grams. So start with the grams of product that was actually made and run back to the grams of the excess reactant. That's the one that gave you the higher number in that previous calculation. That'll tell you the amount of excess reactant that was actually used in your process. Then the problem itself will tell you how much was given or provided. And so the last thing you need to do, this is the most forgotten step, is you need to do a little subtraction problem. You need to take the provided amount from the problem minus the used amount from your stoic problem that we just did, and that'll tell you how much is left. All right, so this is a continuation of the last problem. And this one, we're trying to figure out how much of the excess reactant is left over if 4.5 grams of hydrogen is reacted with 15 grams of oxygen. We already did the problem. We already know how much water can be produced. It was 16.9. So we're going to reuse that 16.9 grams of water here. And we're going to go backwards to grams of hydrogen because hydrogen was our excess reactant. So we're going backwards to hydrogen. We figure out that only 1.89 grams of hydrogen was used. And so we're going to take the amount provided in our problem, which was 4.5, minus the amount that was used from this calculation here, which was 1.89. And that tells me that I had 2.61 grams of hydrogen left over. That means that in the future, if I wanted to save some money, I could use 2.61 grams less of hydrogen if I wanted to still use 15 grams of oxygen. So here's what it looks like all put together. We've got this one reaction, which is the hydrogen and oxygen going to our water. The question asks how many grams of water can be produced if 4.5 grams of hydrogen reacts with 15 grams of oxygen, and it's also asking how much is left over. So my first problems, again, I ran from grams of reactant to grams of product. I figured out that only 16.9 grams of water was actually produced. I figured out that oxygen was my limiting reactant. Hydrogen was my excess reactant. And so to figure out how much was left over, I'm going to start with that 16.9 grams of water that I got from my previous problem. And I'm going to run it back to the grams of hydrogen. I figured out that only 1.89 grams of hydrogen was used. So I'm going to take the amount from my problem, 4.5 grams of hydrogen minus 1.89 to get me 2.61. All right, so in this problem, we're figuring out how many grams of lead 2 chloride, will be produced if 10 grams of lead 2 nitrate is reacted with 5 grams of sodium chloride. We're also going to have to figure out how much excess reactant will be left over. So this is one long problem like the previous slide. The first thing you need to do is balance the chemical equation. Then we're going to find the mass of lead 2 chloride produced by running two different stoich problems, starting with the mass of reactants and going to mass of lead 2 chloride. So these are two mass-to-mass problems. The first one is going to start with the mass of lead 2 nitrate, go to moles of lead 2 nitrate to moles of lead 2 chloride, 2 grams of lead 2 chloride. The second roadmap is going to be grams of sodium chloride to moles of sodium chloride, to moles of lead 2 chloride, to grams of lead 2 chloride. Once you do that, you're going to get two different answers. The smaller of the two is the amount that you can actually make, so that's your answer. And then you should be able to take a look back at those problems, and whatever one produced the lower amount, that's your limiting reactant, and the one that produced more is your excess reactant. Then, using the amount of product made, determine the mass of your excess reactant that is used by running a stoich problem from the product back to the excess reactant. Then you're going to subtract that amount from the amount provided. So if I go ahead and try to balance this, I'm going to need 2 sodium chlorides and I'm going to need 2 sodium nitrates. If I take a look at my math here, on the top of the screen, you are going to see the molar mass calculations. The nice thing here is if you do them first, you can kind of let them hang out up top and then you can use them when we need them. So here are the roadmaps that I talked you through right before. We're going to start with my 10 grams of lead 2 nitrate, and we're going to use the molar mass from up above to get us out of grams of lead 2 nitrate into moles of lead 2 nitrate. Then we're going to use the balanced chemical equation. So remember, it was 1 moles of lead 2 nitrate per 1 mole of lead 2 chloride, so 1 to 1. And then we're going to get out of moles of lead 2 chloride into grams by using that molar mass. So here, if we were to get 10 grams of lead 2 nitrate, theoretically we could produce 8.397 grams of lead 2 chloride. If we were given 5 grams of sodium chloride, we would get out of grams of sodium chloride into moles of sodium chloride. Then we're going to get out of moles of sodium chloride into moles of lead 2 chloride using our mole bridge, our mole to mole ratio, using the coefficients. There were 2 moles of sodium chloride per 1 mole of lead 2 chloride. Then out of moles of lead 2 chloride into grams of lead 2 chloride, hopefully you notice here that this part here is the same in both reactions. So your sodium chloride would be able to produce 11.9 grams, but since that's larger than the other amount, we could only produce 8.397 grams of lead 2 chloride. Now, that's the amount that can be produced. Since lead 2 nitrate was the one that did that, that would be our limiting reactant, and sodium chloride is our excess reactant. Now, we're going to go in reverse. So we're going to start here with the amount that was made. So that's where we're starting here. And then we're going to get out of that as grams into moles. Then we're going to go moles of lead 2 chloride into moles of sodium chloride because that was our excess reactant. And finally, out of moles of sodium chloride into grams of sodium chloride to be our unit there. So we go in reverse. Grams of lead 2 chloride gets canceled by molar mass. Moles of lead 2 chloride gets canceled by the mole bridge. Moles of sodium chloride gets canceled by molar mass. So we're left in units of grams of sodium chloride, giving us 3.53 grams of sodium chloride used. And so then finally, we have to do this subtraction problem, the one that students often forget. We were provided with 5 grams of sodium chloride in the problem. We need to subtract 3.53 grams that we actually only used, and so we're left with 1.47 grams at the end. The last thing we need to talk about is theoretical and actual yields and the concept of percent yield. So the amount of product that can be produced by a reaction as we calculate it in a stoichiometry problem is called the theoretical yield. The amount that actually is obtained is called the actual yield. And oftentimes the actual yield should be less than the theoretical yield. That's because sometimes we have side reactions going on. We have maybe an incomplete reaction, or maybe we have a difficult time capturing our product. So again, theoretical yield comes from math. Actual yield comes from the product, the problem. It would state it in the problem like this much was actually collected, or the actual yield was this, something along those lines. Now, why do we care about that? We can figure out the percent yield. And percent yield really just tells us how much should we have been able to attain compared to how much we actually obtained. So the formula for this is actual over theoretical times 100. Now make sure that the units of your actual and theoretical are in the same units. For example, you need them probably both in grams. Eventually you may need them both in liters, that sort of thing. They need to be in the same units in order to make this work. So actual over theoretical times 100. This is on your reference doc. So upon reaction of 1.274 grams of copper 2 sulfate with excess zinc metal, 0.392 grams of copper metal was obtained according to the equation. So I'm going to break this down for you. This 1.274 grams of copper 2 sulfate, this is our starting of stoich. So that's where we're going to start. And in this case, we are given this 0.392 grams of copper metal. This is our actual yield that we're going to use in the problem. Okay, so we're going to start stoich with grams of copper 2 sulfate, and we're going to end it with grams of copper metal. How did I know that? It's because I was given the amount of a reactant, and then the actual yield copper here is a product. So we're going to go grams of copper sulfate to moles of copper sulfate to moles of copper to moles of, grams of copper, my bad. Grams of copper. So run a stoich problem starting with that 1.274 grams, going to grams of copper, and then that answer will be your theoretical yield. So once you get this answer here, that is your theoretical, which we will then use in our percent yield calculation. The percent yield calculation, we're going to use the actual from the problem and the theoretical from our math. So The molar mass of copper 2 sulfate is up there at the top, 159.62. We run our problem here from, remember, it was going from grams of copper sulfate to moles of copper sulfate to moles of copper to grams of copper. So we were getting out of grams of copper 2 sulfate, out of grams of copper 2 sulfate using our molar mass, getting into moles of copper 2 sulfate. We get out of that and into moles of copper using our mole ratio, our mole bridge from our coefficients, out of moles of copper and into grams of copper for our unit. We should be able to produce 0.5072 grams of copper. This is our theoretical. And then from the problem, remember that this was given in the question, in the problem. So that's our actual divided by our theoretical times 100. We only made 77% of what we should have. Ideally, we always want to get up to 100% for percent yield. It would be always great to produce 100% of what we should be able to, but in reality, that doesn't always happen. So we always want to get to 100%, but sometimes, oftentimes, we don't quite get there. So 77 isn't amazing, but it isn't awful as well.